When looking at doing formula, there is a formula per se that goes into finding circles. And there's going to be a lot of commonalities when we go from circles to ellipses to hyperbolas and other shapes. We call them conic sections as we move through this. But what I'm going to start with is a center at -3, 2, which is right there, -3, 2, with radius of 3. So it's really hard if I move over 3 points, 1, 2, 3, down 3, 1, 2, 3, left 3, 1, 2, 3, up 3, 1, 2, 3. To then try to draw that in, people get some really clunky looking, and I'm not even going to try very hard so you feel better about it when you do it. But that's what I'm doing. But what I want to do is create the equation for that circle. And when we were in class, we went through the distance formula. So really we're looking at the distance formula, or in this case, we're going to say r squared is equal to x minus, and we call it h squared, plus y minus k squared. Why is it h and k? I don't really know, but that's what the mathematicians in the past have really kind of landed on. And what we're saying is h is the x coordinate of the center. The k is the y coordinate of the center. So when I plug this in r obviously is the radius. So I'd have 3 squared equals x minus, and the x coordinate of the circle is -3, so I type -3 squared plus y minus, and the y coordinate is 2 squared. So I end up with 9 equals parentheses x plus 3 squared plus y minus 2 squared. And that's the when we're doing this in center form or in standard form, this is what we do. You could actually, if you wanted to, foil this out and foil that out and make a very giant equation. So it'd be x squared plus 3x plus 9 plus y squared minus 4y plus 4. And then you'd bring the 9 over and you have this whole thing equal to 0. And then you could do all sorts of things with that. All right, but for what we're going to do, we're just going to leave it at this. If you were given this equation, they would ask you a simple question like, what is the radius? The radius is 3 because it's r squared. What is the x coordinate of the center of the circle? It'll be -3. Much like other things, we're saying what makes it 0. This one here, same kind of thing, what makes it 0. All right, and later on we're going to be doing a question. We're going to find the x-intercepts and the y-intercepts, but we'll get to that in just a second. And then they're going to add things like this. Circle with a diameter of endpoints of 2, 10. And immediately I'm always thinking, how can I graph this? So 2 over and 10. I did my axes probably the wrong way. 2 over and 6 up. We'll just kind of call it there. 2 over and 10 up. Plot those 2 points. It says those are endpoints of the diameter. So then I go, all right, well, the diameter cuts across the entire length of the circle with the center at the midpoint. Yeah, so midpoint, then you're trying to remember from geometry. Do I know the midpoint? What does that mean? It means half the distance. Well, that's easier to do than just thinking midpoint. Now, midpoint is the average of the x's and the average of the y's. So the average of 2 and 2, luckily, is 2, because if you add 2 plus 2 and then divide by 2 because there's 2 points, that's 2. The average of 10 and 6, so I go 10 plus 6, that's 16. Divided by 2, that's 8. Or you're just thinking to yourself, how far is it from 6 to 10? It's 4. So halfway up is 2. So that's at 2, 8. So then the formula of my equation would be x minus 2 squared plus y minus 8 squared equals r squared, the radius squared. I did this here, and my diameter distance was 4, so my radius distance is 2. 2 squared is 4. Ta-da! Next slide. All right, we're going to talk about something else related to circles here, and then we're going to jump back to using the distance formula in a second. When I have a circle centered at the origin, we're going to start talking about different angles that occur here, and we're going to call them central angles. We're going to call them central angles because they start at the origin, and then they go out to a certain point on this circle. And that central angle there is going to be using usually a Greek letter like theta. Let's see, so we're going to use theta. We might use, we're going to try to stay away from delta because delta means change, unless I use the other delta, which is that delta. But theta is probably one that we use a lot. Occasionally we'll throw an alpha in there. So if I have something going on, I got two different angles, I need to give them two different Greek letters to use. But we try to stay away from things that have other significant math background. So we're not going to use delta very often. We're not going to use mu. And beyond that, I'm trying to think of anything else that we really want to. Phi, going to stay away from phi. That's the golden ratio. Also not part of content of this class. But we're going to talk about that as a Greek letter theta. So that's that angle theta. If I were to start in this is where we start from when we're talking about angles. So if I'm going to draw an angle that's in standard location, it would be centered at the origin and it goes up from the x-axis. So this theta is going to be something, looks like it's about, I don't know, 35 degrees. So we'll call it 35 degrees. All right. A coterminal angle is an angle in that exact same position that is a different angle measurement. So if I have another angle that's coterminal to 35 degrees, my new one would be, we'll call it delta, would be equal to 395 degrees. You might be thinking, wait, how did we get that? I did one whole circle all the way around. So if I'm here and I go all the way around and I'm here again, starting from here, 395 degrees, it ends at the same place. It's also 35 degrees. So 35 and 395 are coterminal angles. They terminate at the same place, coterminal, same termination points. Okay? So quadrant 1, 2, 3, and 4. Not sure if you remember that in the past. So this is quadrant 1, this is quadrant 2, this is quadrant 3, this is quadrant 4. And it's always relative to the x-axis as a starting point. So 35 degrees up. Where we might see it a little bit more often is like if I draw this one down here, and let's call that angle alpha. And if we say that's equal to negative 60 degrees, it's negative because it's below the x-axis. I'm not going in the same direction. I'm going from, instead of up and around counterclockwise, I'm going clockwise. Going clockwise is negative rotation. And for those of you that take physics later on, we'll remember how and why that is. But anyways, clockwise is negative rotation, so negative degrees. Negative 60, it's coterminal. If I go all the way around, 90, 180, 270 plus 30 would be 300 degrees. So negative 60 degrees, 300 degrees are coterminal. Coterminal. All right, going on to the next slide. I guess I'm not going to do the circle thing. We'll come back. So then what we're going to start looking at is looking at units of measurement that are no longer in degrees. And we're pretty much going to stay there for the rest of this class and through all of calculus and beyond. We're going to stop using degrees. We're going to start using radians. A radian is a unit of measurement of an angle, but it's not in degrees. So how it's related, it is related to, so if I just draw this in here, I'll use blue again. This one right here. I'm going to call this angle here theta. All right, that theta in radians is equal to the arc length, this length right here, all right, divided by the radius. Now, if you don't remember how to take arc length, some of you recall that the diameter of a circle is equal to pi d. Sorry, not diameter. The circumference is equal to pi d. That is the distance all the way around. So the arc length, my arc length, is equal to a portion of the circumference. How much of the circumference? I want to take pi 360ths of the circumference. Sorry, pi, theta. See, I'm getting all my letters mixed up. That's a theta. So if I take theta, this is not quite a complete circle. So this portion of the whole circle, and then this portion of the whole circumference as a ratio. But what does that mean? That means if I take the arc length and divide it by the radius, it gives me radians. For example, 30 degrees. If I do 30 degrees, and I'm going to go ahead and get rid of this for a second, and do 30 degrees. This is 30 degrees. How much of a circle is 30 degrees? All right, so if I'm looking at this circle here, I see that my radius is 1, 2, 3. My diameter is 6, and that means my circumference is equal to 6 pi. So it will be 6 pi divided by 30/360ths, which is 1/12. All right. Multiply. I got too many fractions going on here because in my original equation back here, it's not this, sorry, it's times. Circumference times theta over 360 because it's the fraction of the circle. Apologize on that one. All right, so the circumference of a circle times pi over 360, because pi over 360 is how much of the circle I want to use. I'm using 1/12. So it's times 1/12, and that will give me, I am running out of room on my little edge here. Hold on just a minute. So it's pi over 2. All right, but that's not radians yet. That's my arc length. My arc length is pi halves, and then I have to divide it by the radius. My radius in this circle is 3, so it gives me pi 6ths. It's a lot of rigmarole to run around in, but what we're going to find is regardless of the radius length, the radians will be the same. Every circle, 30 degrees, the radian measurement is pi 6ths. All right, 45 degrees will be pi 4ths. 60 degrees will be pi 3rds. 90 degrees will be pi halves. And really what's going on is I'm just going up and around. And in a full circle in radians is 2 pi. So 360 degrees is 2 pi. Quarter way around is pi halves. This over here would be pi. This would be 3 pi halves, and that would be back to 2 pi. The reason why we're doing this is when we get to more time with sinusoidal curves, so sine, cosine, tangent, cotangent, cosecant, and secant, that's where we'll start. We're going to find that there's a lot of patterns that go into that, and once I remember a few of these, they all just kind of follow suit. So 30 degrees, 45 degrees, so this is pi 6ths, pi 4ths, 60 degrees, pi 3rds, this is pi halves. And then you do this one, halfway out is the 45. I'm getting really sloppy with my lines. And then it would carry on in terms of those same fractional increments as it goes up. But radians will be basically, now that we're kind of going through this, we've shown it once. We're not going to spend a lot of time calculating radians out. We're going to get in the habit, and then these are going to be my most common ones. And then you're going to get to, this is 3 pi 4ths. Over here is pi. You're going to have 2 pi 3rds, which is that one there? I can't, no, wait. Anyways, I'm running out of space on my little board here, and it's just getting messy as I talk. So we're going to fill all these in a little bit later. And then we're going to get to something that's the most spectacular thing in the world called the unit circle. Next slide. And then the last little portion for today is sector area. So if I want to find the area of a sector, let's see if I can get this to actually work for me here. Let's fill it in with green. Nope. I need to trace over that. Now let's see if it'll let me fill that in. There we go. So that sector area is equal to 1/2. So the area is equal to 1/2 theta times r squared. All right, and theta would be whatever that angle is. In radians, we're doing that. So that's how you do area of a sector. If you know the angle that's in there, times r squared times a half, and that's going to be your area. I could derive that for you, but I'm not going to. It's actually closely related to the complete circle area, pi r squared. And when you convert theta into radians, you're going to see what happens with the pi's. But anyways, that's how it would connect to what you've done in the past where you remembered, oh, area of a circle is pi r squared.